And have you ever pondered the significance of pi ligands in chemistry? Today, we're unraveling the mystery behind these unique entities that hold immense importance in the realm of chemistry. Pi ligands, also known as pi acceptor ligands, are intriguing in their structure and function. Their unique structure with their parallel p orbitals allows them to form chemical bonds in a fashion that is quite different from sigma bonds. They are an integral part of the chemical bonding process, especially when it comes to the formation of complex compounds. These compounds, in turn, play a crucial role in various chemical reactions, but the intrigue doesn't stop there. Pi ligands are not just about forming bonds and creating complex compounds. They are also about the fascinating interactions that occur at the atomic level, leading to properties and behaviors that are nothing short of mesmerizing. As we delve deeper, the fascinating world of pi ligands is sure to astound you. To understand pi ligands, we must first grasp the concept of ligands and chemical bonding. So what exactly is a ligand? In the simplest terms, a ligand is a molecule, ion, or atom that binds to a central atom to form a complex. This binding process is known as chemical bonding. Ligands can be a single atom like hydrogen, a simple molecule like water, or a complex molecule like an enzyme. They play a crucial role in many chemical reactions, acting as catalysts, inhibitors, or even signal transmitters. Now, there's an assortment of ligands, each with its unique characteristics and functions. But today, our focus is on a special type known as pi ligands. These ligands are more than just spectators in the chemical bonding process. They actively participate in the bonding, contributing their pi electrons to the central atom. This is where pi ligands stand out from the rest. Most ligands form bonds using their sigma orbitals, the simplest type of atomic orbital. Pi ligands, on the other hand, use their pi orbitals, hence the name. These orbitals are more complex and can overlap in different ways, leading to unique types of bonds. Moreover, pi ligands have a unique ability to donate and accept electrons simultaneously, a characteristic known as ambidentate. This ability makes them incredibly versatile in chemical reactions, opening up a world of possibilities in the field of chemistry. In essence, pi ligands are the rebels of the ligand world. They refuse to follow the traditional sigma bonding route, opting instead for the more complex and versatile pi bonding. They're the ones pushing the boundaries, exploring new territories, and constantly surprising us with their capabilities. Now that we have a basic understanding of ligands, let's dive into the world of pi ligands. In the universe of ligands, pi ligands hold a special place. They are the star players in the world of chemistry, with unique abilities that set them apart from their sigma counterparts. To truly appreciate pi ligands, we first need to grasp the notion of pi bonds. Just like a handshake, a bond is a connection. In chemistry, it's a connection between atoms. The strongest and most common type is the sigma bond. It's like a firm handshake right down the middle. But imagine if you could shake hands from the side as well. That's essentially a pi bond. It's an additional connection, a side-to-side overlap of atomic orbitals that strengthens the bond between atoms. This is where pi ligands come into the picture. They're like the hands in our handshake analogy. A pi ligand is a molecule or ion that can donate one or more pairs of electrons to form these pi bonds. They're like generous friends, always ready to lend a hand, or in this case, an electron pair. But what makes pi ligands so special? Well, it's their ability to form these pi bonds that sets them apart from other ligands. While most ligands can only donate electron pairs to form sigma bonds, pi ligands can donate electron pairs to form both sigma and pi bonds. This makes them versatile players in the game of chemistry, capable of forming stronger, more stable complexes. So, you might be wondering, where do we find these pi ligands? Well, they're more common than you might think. They're found in many organic compounds, including alkanes, alkynes, and even aromatic compounds like benzene. With this knowledge of pi ligands, we're ready to explore their role in chemical reactions. Remember, in the world of chemistry, it's not just about the strength of the bond, but also about the ability to form connections. And in this game, pi ligands are the star players. Pi ligands are not just theoretical constructs, they play a crucial role in many chemical reactions. They are the unsung heroes of the chemistry world, driving reactions and facilitating the creation of new compounds. Let's dive right in and see pi ligands in action. At their core, pi ligands are electron donors. They generously offer up pairs of electrons to metals, forming bonds and catalyzing reactions. This seemingly selfless act is what makes them such pivotal players in the world of chemistry. A prime example of this is in the formation of complex compounds. In these scenarios, pi ligands act as the middleman, bonding with a metal atom and setting the stage for other elements to join the party. Without pi ligands, these reactions simply wouldn't happen, highlighting their fundamental importance in chemical processes. Let's consider a real-world example: the formation of ferrocene, a compound that revolutionized our understanding of chemical bonding. Here, two cyclopentadienyl anions act as pi ligands, donating their electron pairs to an iron atom. The resulting sandwich structure, with the iron atom wedged between the two anions, is nothing short of a molecular masterpiece. This is pi ligands doing what they do best: facilitating complex bonding arrangements and enabling new forms of molecular architecture. Another key area where pi ligands strut their stuff is in catalysis. In reactions like olefin metathesis, pi ligands support the transition metals in their role as catalysts, helping to speed up reactions and increase their efficiency. But despite their role, pi ligands are often overlooked, with the spotlight falling on the more glamorous transition metals. However, without the unsung pi ligands, these metals would be unable to fulfill their catalytic roles. In these ways, pi ligands are like the stagehands in a theater production. They work behind the scenes, setting everything up perfectly for the stars to shine. But their role is no less important. In fact, without them, the show simply couldn't go on. Pi ligands, as we see, are not mere spectators, but active participants in the drama of chemistry. The influence of pi ligands extends beyond the realm of chemistry. Diving into the real-world applications, pi ligands play a pivotal role in various fields. Their impact is not just limited to the periodic table or the chemistry lab, but extends to industries, medicine, and environmental science. Understanding the core concepts of pi ligands can truly lead to advancements in these fields. Let's start with medicine. Pi ligands are key components in many pharmaceutical compounds. They can bind to metals in a specific way, making them ideal for creating complex structures found in many drugs. Imagine a world where diseases become less of a threat just because we understand how these tiny entities function. It's fascinating, isn't it? Moving on to the industrial sector, pi ligands are instrumental in catalysis, a process extensively used in industries, especially in the manufacture of polymers. They facilitate reactions that might otherwise be slow or not occur at all. This not only increases efficiency, but also reduces costs. So every time you see a plastic product, remember pi ligands might have had a role in its creation. Now let's talk about environmental science. Pi ligands play a crucial role in the reduction of harmful pollutants. They help in the conversion of harmful gases into less toxic substances, making our environment cleaner and safer. Who knew that these microscopic entities could have such a macroscopic impact, right? It's clear that the impact of pi ligands is far-reaching. They might be small, but their influence is mighty. They help us build life-saving drugs, manufacture everyday products, and even protect our environment. Understanding their behavior and properties is not just crucial for chemists, but for all of us. We might not see them, but they are there, silently shaping the world around us. From the smallest atom to the largest industries, pi ligands indeed leave a significant mark. To sum up, pi ligands are an integral part of the chemical universe. We've journeyed through the fascinating world of these atomic entities, unveiling their intriguing properties and roles. We started by defining what pi ligands are: tiny yet powerful agents that form unique bonds with metal atoms, contributing to the stability and functionalities of many complex compounds. We then delved into their role in chemical bonding, highlighting their ability to donate electron density to metals and create metal ligand bonds. This unique bonding capability is what sets them apart, allowing for the formation of various compounds with distinct properties. Furthermore, we explored their impact across various fields. From the pharmaceutical industry to material science, pi ligands are instrumental in the synthesis of many compounds that we use and encounter on a daily basis. Next time you come across a complex chemical compound, remember the humble pi ligand that might be playing a pivotal role in its existence.